My name is Terence Walk. I'll start with the introductions. Spam is an evolving adversarial problem. Phishing, malware, and scam keep changing. Attackers adapt with tricks like obfuscations, domain rotations, and image-only email. Our goal is high precision and strong recall, so real emails aren't blocked while new threats are caught. We treat this as an evolving system, detect data drift and refresh model, not a one-off accuracy chase. Our problems and our objective: spam takes a large share of global email traffic and cluster inboxes, leading to real risks like phishing, fraud, and malware. The core issue is that tactics keep improving, so filter must adapt. Our goal is to build an adaptive, learning-based model that stays effective and robust over time until a newer model replaces it. Methodologies. We run two comparisons. First, a model comparisons across traditional machine learning, deep learning, and transformer. Second, a hybrid comparisons by comparing model with another model and comparing own original model with tweaked model. The model that we use, multi-nominate bias, very fast on word counts, good for spark text. Logistic regressions, output calibrated probabilities, ideal for threshold tuning. Linear SVM, strong max margin classifier in high-dimensional text. We calibrate score when we need probabilities. Random forest capture non-linear patterns and outlier. It features importance, but it's heavier in memory. LSTM-BERT learns sequence and pre-trained semantics. Better accuracy if we have compute, but higher latency and lower intrinsic interpretabilities.
Emails from group 15. I'll start off with the solutions, evaluation, and discussion part for the presentation. So the ground settings. Next, you have the model and architecture settings. So for datasets, the similarities will be with the phishing email dataset, which from the link. And from classes, the similarity will be ham 0 and spam 1, so unwanted and wanted emails. Next, we have the total samples. So for similarities, a total of 39,154, so ham has 17,312, spam has 21,842. Next will be train and test speed. So for differences, train is 0.8, test is 0.2. Train is 0.7 and test is 0.3 for LSTM only. So for random speed, the similarity will be 42. For batch size, the differences is BERT Mini 16 and similarities will be traditional mono 512. So as the deep learning model. Next is the epoch. Differences is BERT Mini 15, LSTM will be 20. Next, we have the pre-processing settings. So for false lowercasing, the description is that it converts all text to lowercase, ensuring all words are treated the same and reduce the feature repetition. Next will be URL remover. It uses a reject, so like http/s capital S plus, as it might affect the accuracy of the test. Next is the punctuation remover. It strips symbols such as exclamation mark, question mark, full stop, and focus on analysis on actual words instead of formatting. Next is the tokenization. It split text into individual words using certain tokenizer from NLTK library and enabling further processing of words. Next will be the stop word remover. So remove common English words, as like, the, is, and of. So focus on focus on meaningful terms. Next is the rejoining tokens. So it joins clean tokens back into a single string. And the lastly is white space normalization. It removes extra or irregular spaces to keep the text clean and standardized. Next, for the exploratory data analysis, as you can see, the distribution of spam and legitimate emails. So ham has lesser and spam has more. So spam 55.8% and the ham is 44.2. So the most common words in spam emails is 10, and the most common words in legitimate emails is submission ID. Next will be the top 10 common diagrams in text data. So as you can see, the most common one is submission notes, and that will be all. Thank you.
Hi, my name is Jala from Group 15. In this session, I will present our traditional machine learning baseline on CEAS email dataset and highlight what they tell us about precision, recall, and especially false positives, which for our use case, how mistakenly sent to spam, are the most costly. We evaluated four models: naive Bayes, random forest, SVM using SGD, and logistic regression using precision, recall, F1 score, accuracy, and their confusion matrices. Keep in mind that reducing false positive is our priority. As a quick preview of the result, random forest performed best overall, followed by logistic regression, then SVM with knife bias. Knife bias achieves 88.38% on precision, 87.49% on recall and accuracy, and 87.53% on F1 score. From the confusion matrix, we see 223 false positive and 757 false negatives. The takeaway is that although knife bias is fast and simple, its independence assumption limits expressiveness, leading to higher FP and FN than other models. Moving on to random forest delivers the best overall performance with 98.44% on precision, recall, F1 score, and accuracy. It keeps errors low at 53 FP and 69 FN. This makes it our strongest option for minimizing ham being flagged as spam, with the trade-off of heavier memory usage and slower training and inference compared to linear models. The SUM trained with SGD reaches 96.63 on precision, 96.6 on recall F1 score and accuracy, with 188 false positives and 78 false negatives. It's a solid linear baseline, but the false positives are higher than random forest and logistic regression. We could tune the decision threshold to push precision up if reducing FP is critical. Logistic regression scores 97.32% on 4 of them. It records 117 false positives and 93 false negatives. This put it close to random forest while remaining much lighter to deploy, and the calibrated probabilities are helpful when we need confidence score for risk tier action. Overall, we recommend random forest as the primary baseline with logistic regression as the lightweight alternative.
Hello, my name is Kwan Yu from Group 15. I will be presenting the approach and output of long short-term memory model, a deep learning model that mainly uses neural network to train and test dataset with. The dataset that will be used is the conference email and anti-spam dataset from 2008. In this model, I had chose to use a pre-designed model from Sogo 11 as I want to see how our dataset works with pre-designed model and if the dataset we chose is able to work with this model. To ensure that the dataset of choice can be fitted smoothly, I edited some parts of the code but still maintain the model's originality. Besides that, I have 4 other iterations of the original model, all tweaks in some ways to see if the model can still achieve high accuracy throughout the test. The next 5 slides contains the outcome and of the base model and 4 other tweaked models. Here is the result of the baseline model. It contains the originality of the model and no tweaks has done in it. Next is ablation A, which has no data preprocessing in the model. This is where I had removed all data preprocessing features from forcing low casing to tokenization from the model. Moving on to ablation B, which includes vocabulary reduction to the model. I changed the max features, which controls the maximum number of unique words to keep for training the model from 5,000 to 1,000, and max length, which controls the maximum number of tokens per text sample, either truncated or padded from 500 to 100. Now to ablation C, which includes model architecture changes to the model. I increased the cross layer from 64 to 128, which also increased the commutation of the model and dropout rate from 0.1 to 0.5, increasing the percentage of words being ignored in the model when the test is running. Lastly, ablation D, which added training parameters changes into the model. Here, I dropped the batch size from 512 to 128 to increase update per epoch when it runs and increase the early stopping patient from 3 to 5, allowing the model to test more before being stopped. From the summary table, we can see that ablation A has a higher accuracy score than the original baseline model, while other ablations fall short due to the tweaks that may under or overfit the dataset, resulting in the fall off of the accuracy. However, all 4 tweaked models are still pretty high, averaging at 98.9%, showing that the LCM model actually able to detect and classify spam from ham even when using another dataset.
Hi guys, my name is Junlok and now I'll be going to present about the transformer model, which is BERT Mini. In this project, we built a mini BERT spam classifier that reads each email subject and body. It used a transformer's self-attentions to weight the most relevant words in context, then summarize the emails and predicts a probability for spam versus ham. We fine-tune the models on our label data with class weights, cross entropy to handle the imbalance, and monitor a validation split each epoch. So these slides show the results of our models. So as you can see on the test sets, it reached 99.8% accuracy, 99.86% of precision, 99.77% recall, and last one is the 99.82% on F1 score. And the confusion metrics show that 1,728 true negative, 2,180 true positive, 3 false positive, and 5 false negative out of 3,916 emails. This means that false alarms and missed spams are both extremely rare, and in deployments, we can tune the decision thresholds to favor even higher precision or higher recall depending on the policy.
Hi, my name is Tan Shua Mingyu and I'm going to present finding and takeaways. So for insight on deep learning model, LSTM, our LSTM works best with no pre-processing. F1 score is 99.55%, accuracy is 99.5%. The reason is that spam signal live in the noise like the triple exclamation marks, HTTP, links and triple dollar sign. When we change batch or architecture, training got less stable and accuracy didn't improve. So why reduce vocab or length hertz? It's shrinking vocab from 5,000 to 1,000 and length from 500 to 100 hertz because we lose rare but important tokens, truncate let queues like unsubscribe lines, and make embedding less expressive. Net drop is more around about 0.3%, but it's still consistent. The model is still strong. What to keep versus remove? For keep the signal, punctuation burst, currency symbol, all links or domain numbers and casing. For do only, light cleaning like overcasing. Besides, in span, noise is signal. Its over cleaning deletes discriminative features. For cross-family result, across model, random forest reaches about F1 score accuracy around 98.44%. Our best deep model, no pre-processing LSTM, get F1 score 99.55%. Overall, winner is BERT Mini, accuracy 99.77%, precision 99.86%, and recall 99.73%. The F1 score is 99.79%. There is around 1.7 false positive per 1K hem. In conclusion, dataset is highly separable, extra complexity didn't buy gains, deployed with a threshold tuned for high precision at high recall. Keep processing light and monitor drift for periodic drift training. Thank you.